So Unit 6, Chemical Kinetics, is a very quick, short unit. So make sure that you're writing down any questions that you have and let me know what those are so we can clarify any issues that you might have with this unit. So the first thing is that kinetics, the word is based on the word kinesis, which just means movement. And in chemistry, we talk about the kinetics of a reaction, so how fast that reaction is going, and not just how fast, but how can we improve that speed? How can we make it go faster? How can we improve the yield of that reaction? And so rate of reaction, the rate is defined as the change in concentration over the change in time. And the units are moles per decimeters cubed, which is your concentration, per second. It's usually seconds. You could see other varying amount of time, but it is usually seconds because reactions are typically fast like that. As the reaction proceeds, your reactants would decrease and your products would increase, meaning that the rate for a reactant should be negative and the rate for the product should be positive. Now, when you do your change in concentration divided by change in time, you might not get a negative value. You have to put that negative there, showing that it's decreasing at that rate, or a positive sign to show that it's increasing at that rate. So if we were in class, we would do a lab and we would be able to graph the change in concentration over the change in time, and produce something that looks like this. And from that graph, we can get the rate. We can calculate the rate. So the steepness or the gradient of the curve is what we're measuring when we measure the rate, because it's the change in concentration over the change in time. Now we get the instantaneous rate from this. So it's not a straight line. So it's not going to have a continuous rate. It's going to change as you're going throughout it. So it's an instantaneous rate, the rate at that precise moment in time. Notice that on this graph, it is a negative slope, which would represent or tell us that this substance is a reactant. So how do you find the instantaneous rate? You have to draw a line that is tangent to the curve. So here at time 600 seconds, we have drawn a line there, and from that line's slope, we can get the instantaneous rate. The rate is the greatest at the start, so your slope is steeper up here than it is when you continue on. And that's just because when there's no products, there's reactants there. The reactants can react faster. There's nothing in the way. All right, so how do we measure rate? Tomorrow, or in the next lesson, you are going to look at 6 different ways at which we can measure the rate of a reaction in a lab setting. And depending on what the reaction is, you would choose from one of those 6. All right, a little bit of review, and this goes back to Unit 1, Kinetic-Molecular Theory of Matter. So it's based on the fact that matter is always moving. So our particles are always in motion. They always have some type of kinetic energy. Even solids that are just vibrating slowly in place, they're still moving. The movement is causing some collisions to happen. Not all of the particles of the substance have the same kinetic energy at the same time, so there's a bit of randomness there. Absolute temperature is the average kinetic energy of the substance. It's measured in Kelvin. As you increase temperature, you're increasing the rate or increasing the kinetic energy. So there's a direct relationship between temperature and kinetic energy. Maxwell-Boltzmann distribution curve that shows the particles in a gas at a particular temperature and how it relates to the kinetic energy. The area underneath the curve represents the total number of particles. So there's more particles with this kinetic energy than there are down here. On the curve, it also shows us the activation energy. Remember, that's the energy needed in order for the reaction to take place. So we can look and see how many particles, or what's the area underneath that curve, how many particles would have that amount of energy to make the reaction occur. Now there's two curves on here representing two different temperatures. So the red curve, or the second curve here, has a wider area, and that's to show that it's at a higher temperature. So at a higher temperature, you have more particles with this amount of energy. So that's why it looks like a wider curve. The activation energy doesn't move on this line unless you're adding a catalyst. So that it would be the same for that reaction at the two different temperatures. But you can see that the amount of particles that have that amount of energy does change. That area changes. So we would have more, this red curve would have more particles occurring at that temperature. So there have been questions that ask you to draw the Boltzmann or the Maxwell-Boltzmann distribution curve, what a higher temperature would look like. So you just want to make sure that the curve is shifted to the right, that the peak of the curve is a little bit lower, and that it only crosses it one time. So here is where they cross. They do not cross down here towards the bottom. So that is some important things to note there. All right, collision theory we talked about last year. First thing is that for a reaction to occur, the molecules have to collide. So your reactants have to collide together in order for a reaction to take place. They have to have that amount of energy, which we call the activation energy. And then they have to collide with the correct orientation. So again, the three things you have to have is a collision. You have to have that collision with enough energy to make those bonds break and form. And then you have to collide with the right orientation. So looking at activation energy, it's the energy necessary to overcome the repulsion between the molecules. It breaks the bonds of those reactants. And with enough energy, reactants can achieve a transition state. That's like an intermediate. It's not a reactant. It's not a product. And that can be shown on these graphs at the top of the hill, if you will. So with these graphs, you should already know that this one would be exothermic because we're decreasing in energy, and this one represents endothermic because you're absorbing energy. We talked about that in Unit 5. What we're adding to this is the activation energy. So that's the amount of energy needed to go from the reactants up and over to the products. You can also talk about the reverse reaction. So the activation energy, or the energy needed for the products to reform the reactants. But it's that height from where you're starting to the top of the hill. The red line here, or the energy released or the energy absorbed, that's your enthalpy of reaction. So that's your delta H, just like from the last unit. This one would be negative. This one would be positive. All right, orientation. Since collisions are random, particles will be hitting each other in different orientations. And it can be crucial for some reactants, not all reactions, but some of them. How the reactants are hitting each other becomes important. So here we have nitrogen monoxide reacting with ozone to form NO2 and oxygen. And we can see that these two orientations, no reaction occurs. They have to collide with each other in this type of orientation in order for the reaction to occur. So it's important for this reaction. It might not be for others, but it is something to consider. All right, so how can we increase the rate of the reaction? There's different ways of increasing rate. But what you're doing in all of those circumstances is you're increasing the chance that a collision would have the amount of energy needed, your activation energy. You're just increasing the amount of times particles are colliding. So if you can increase the number of collisions, then you're increasing the chance that they have the correct activation energy, and you're increasing the chance that they are hitting each other with the correct orientation. So it's all about creating more collisions. So the first thing that we have is temperature. If you increase temperature, then your molecules are already going to have more energy. So there's more of a likelihood that they have that activation energy needed for the reaction to take place. So you have more effective collisions. Concentration, the more stuff you have, the more chance there is for a collision to take place. So you're increasing that chance that they're going to hit each other with the right energy at the correct spot, just because there's more collisions happening. Particle size, so if you decrease the surface area, then you're creating more of a chance for them to collide and hit each other in the correct orientation. So the probability just is increasing with a decrease of surface area. So we don't really want our reactants to be in a cube solid state. We want them to be crushed to increase that surface area, that chance of reacting. If your reactants are gases, so you might want to make a note of this, it has to be gases. You can also use pressure as a way of increasing the rate. So if you increase pressure, you're forcing those gas molecules to become closer together. There's going to be more of a chance for them to react. And the more collisions there are, the more chance there is of an effective collision or an effective reaction there. All right, catalyst. If you use a catalyst, that is going to just give it a different pathway. So in our graph that we have, our potential energy diagrams, this blue curve at the top here would represent a non-catalyst reaction, and then the red is the same reaction but with a catalyst. So we're just offering the reactants a different pathway to get to the products, and it would have a lower activation energy. So when we say that a catalyst decreases the activation energy, what we're really saying is we're just giving it a different path with lower energy to create those products. Remember, the catalyst is not a reactant and it's not a product. It's just offering that alternative pathway. And one of the better known catalysts, or a catalyst that you should be aware of, are enzymes from biology. Those of you taking biology, you should be talking about this. Those of you who only took it in the 9th grade, you should still be familiar with what an enzyme is. But you have the enzyme, you take the substrate, and then you can produce those products. So that's one of the uses of a catalyst in biological reactions, biotechnology. That's the end of this whole topic. So if you have questions, make sure you reach out.